Gravity. It is one of the most fascinating and prevalent physical phenomena around us. Yet, not many people knew about it actually until the year 1687. That was the year when Isaac Newton, yes you, get down here, published his laws of motion along with his revolutionary theory of gravity in his book Philosophiae Naturalis Principia Mathematica. According to him, the force of gravity was directly proportional to m1 into m2 by r square, or equal to with a constant g. Newton had no idea what this constant was. I mean, he had a rough estimate for the radius of the earth, 6363.63 kilometers, and he knew about the mass of the sun, but that wasn't helping him at all. Enter Henry Cavendish, who in 1798 shocked the scientific world by figuring out the density of the earth. But how does that help us in finding the value of g? The density of the earth is equal to the mass of the earth divided by the volume of the earth, 4 by 3 pi r cubed for a sphere. But while we can find out the volume, what about the mass? To figure out the mass, Cavendish borrowed Newton's equation of gravity. Then he altered it to form mass equals to Fg times r square divided by gm. And while three of these values can be easily found out, what about g? Even Newton couldn't figure out the value of g. Well, fret not, because our friend Henry Cavendish was a very lucky man. You see, he had a friend known as John Michell, who was undoubtedly one of the most underrated scientists of the 19th century. Well, when John died in the year 1793, he left behind a gift, a torsion balance. A torsion balance is basically a fancy term for two balls on the ends of a beam hanging with a wire from the ceiling. But how will this help us? Well, to find the density we need the mass, and to find the mass we need g. Dealing with all three of these is a bit hard, so let's just focus on two of them for now. Well, g is a constant, so there's no changing that. But mass. The mass is only constant for the object it belongs to. So, theoretically, we could easily replace the unknown masses in the equation with our known masses and still get the value of g. And that's exactly what our good friend Cavendish did. He placed two lead balls on either ends of an iron beam. Each of these balls weighed 10 kilograms. Then he placed two even larger lead balls beside them. Each of these weighed 106 kg. Now because of this, the smaller lead balls moved towards the larger balls due to the gravitational attraction. He did this to induce what's known as a torque. Torque is basically the rotational version of applied force. In this case, torque is equal to the force of gravity multiplied by the length of the beam, but it can also be written as the coefficient of torsion times theta. Theta is the degree by which the beam turned. Now that we have identified our sides, it's time to write them down in an equation. We get k theta is equal to g m1 m2 times L divided by r square. You know, I could have ended the video here if I knew the value of kappa, but we don't. To find the value of kappa, we need to measure the time it took for the beam to oscillate. The time period of the beam is equal to 2 pi times root over the inertia of motion divided by k. Here we meet a new term, the inertia of motion. It's basically a measure of how much a body can resist torque. I is basically equal to 2 times m times L by 2 whole square. This can be simplified further and written as m times L square divided by 2. Substituting all the necessary values, we get 2 pi times root over ml square divided by 2 kappa. Now, it's time to cross the final hurdle. and calculate the value of g. To solve for g, we need to do two things. A. Solve for the value of the time period, and B. Evaluate the original equation k theta is equal to Lf. Now, if we substitute the time period equation, we get this massive jargon. And I don't know about you, but that damn square root, it really pisses me off. So, let's get rid of it, shall we? T square is equal to 4 pi square times ml square divided by 2 kappa. Rearranging, we get kappa equal to 4 pi square times ml square divided by 2 times time period square. And now it's finally time to return to k theta is equal to Lf, the original equation. After substituting all the values, we come face to face with this massive string of variables, which is quite confusing and difficult to look at. But after all that's said and done, we only need to cancel it out. After cancelling and rearranging everything, we are left with g is equal to 2 pi square times Lr square theta divided by m1 times t square. And the value of this wonderful constant is 6.67 times 10 to the power negative 11 meter cube per kg second square.